So volumes of revolution is one of the most challenging topics for students regarding to integral calculus. The definition of the volume of revolution is a revolution solid is formed when one rotates a plane figure above the x-axis revolution. What do we mean by this? We have a function y equals to del f of x, and we have an area under the curve bounded by the limits a to b. If we rotate that area under the curve 360 degrees about the x-axis of the Cartesian plane, we obtain a geometrically alike solid. In this case, it looks like a cylinder. It is important to note that when we deal with volumes of a revolution, we keep using the same original limits of integration, and we treat the situation as if it were a definite integral. The only difference is that we square our gradient function and then proceed to integrate. After this, we incorporate our limits into the integrated function, and we subtract them, upper limit minus lower limit. The end result we multiplied by pi. The volume of our solid form is given by the following function. Pi times the integral from a to b, little f of x squared differential x. This is a sample problem from volumes of a revolution. The function little f of x equals x cubed plus x squared crosses x points at points a, 0,0 and points b, 7,392. The region enclosed by the graph of little f of x is rotated 360 degrees about the x-axis. It is rotated. Find the volume of the solid that is formed by such a rotation. Firstly, before attempting the problem, we need to know that the volume of revolution formula is given by the following. Where pi times the integral of a to b, little f of x squared differential x, where a and b are limits of integration. We first form our volume of our revolution equation with our known limits. Firstly, we proceed to expand our function little f of x since it is squared. As shown in that step, we achieve the following result: x to the 6th plus 2x to the 5th plus x to the 4th. Then we proceed to integrate this result using the power rule. After we have integrated the function, we do not multiply the integrated function by pi. Firstly, we apply our limits, first top limit, then bottom limit, and our end result we multiply it by pi, and that will yield a volume. After performing the necessary operations with the limits and the subtractions, we obtain that our end result is 160,226.73. That result we multiply by pi. Never forget that you need to multiply your end result by pi. Therefore, the volume of the solid form is 160,226.73 pi centimeters cubed. We use centimeters cubed because we are always dealing with volumes. We need to use the arbitrary units centimeters cubed. These are some key definitions regarding kinematics, which is one of the most significant subtopics of integral calculus. The first definition corresponds to velocity. Velocity is the speed at which something moves in one direction. Acceleration is the rate of change of the velocity, in other words, the derivative with respect to the velocity in time of an object with respect to time. Distance is a scalar quantity, referred to the amount of ground an object has covered. We have here the graph of time versus distance, where the distance equation is st equals t minus sine 2t. The y-axis is distance and the x-axis is time. Here we have the time versus velocity graph, where the velocity function is vt equals 0.66 times the quantity t minus 2 squared plus 1.66, where the y-axis is velocity, x-axis is time. And finally, we have the time versus acceleration graph, where the acceleration function is at equals 0.5 minus cosine 3t, where the y-axis is acceleration, the x-axis is time. This is some basic understanding of kinematics related to integration. The integral of vt dt, where vt is a velocity function, equals st plus c, where st is the displacement. The integral of at dt, where at is acceleration function, equals vt plus c, where vt is velocity. Note that the notation for an acceleration function is at, for a velocity function is vt, and for a displacement function is dt. We will provide a follow-up for this notation importance in the next part of the video. Thank you.